Welcome to Factoring Polynomials with a Visual Guide. This is already part 9 of a series of videos to help students understand factoring polynomials completely. It's time to apply all that we have learned for the past 8 or so video lessons. You can skip ahead to a specific item. Click the timestamps in the description below to proceed to the question of your choice. Remember that factoring is like breaking down a number into its prime components, but we're doing it with algebraic expressions. It's an essential skill for solving more complex equations. Now, following our visual guide here, we review the steps in factoring completely. Step 1. Look for the greatest common monomial factor. Now, the very first thing you should always do is check for the GCMF. It is the largest term, number, variable, or both, that divides evenly into every term in the polynomial. So, pulling out the GCF simplifies the problem. Step 2. Identify the type of polynomial. After you've pulled out the GCF, look at the remaining polynomial. Its structure will tell you which factoring method to use. So it can either be a binomial, 2 terms, or a trinomial. If it's a trinomial, swerte ka pag ang leading coefficient mo is 1. In that case, you just need to ask the question, what are the factors of C with sum equal to B? Now, in case the leading coefficient is not equal to 1, hope and pray it's a PST. Kasi pag PST, kahit medyo malaki yung mga numerical coefficients mo, you can factor it ng mabilis. Well, if it is not a PST, okay lang because you can use AC method with grouping. Or, of course, you can always use organized listing, which can actually factor any trinomial. Medyo mahaba nga lang gawin. Now, if what's left after getting the GCMF, the greatest common monomial factor, is a binomial, you have 2 cases. Ang first case is a difference of 2 squares. Madali lang, bakit? The first thing on your mind should be plus minus. And then, put the square roots of the first and the second term of our difference of 2 squares. Done! Remember though, that if you have a binomial with 2 perfect square terms, you can only factor if it's a difference. If it's a sum of 2 squares, it's a prime polynomial. That cannot be factored na. Next case, what if you're given the sum or difference of 2 cubes? This is the only factoring technique na ang factors niya are a binomial and a trinomial. Of course, we have discussed this already. Just remember the SOAP acronym. It will guide you on what operation to use. Finally, what if what is left after getting the GCMF is a polynomial with 4 or more terms? We would be using factoring by grouping. Now we're ready to factor some polynomials completely. Let's look at example number 1. What if we're asked to factor completely 5a cubed minus 20ab squared? So according to our visual guide, the first thing that we should do is look for the GCF, the greatest common monomial factor, kung meron. In this case, by observation, 5 and 20 have a GCF of 5. That's the numerical coefficient of our GCF. And looking at our literal coefficients, A is a common variable, while B is not. So, yun na yung GCF. You factor that out, resulting to a factored form of 5a, that's the common monomial factor, times the quantity a squared minus 4b squared. You can check, of course, by distributing 5a. Now, let's see if we can factor this further. Let's copy 5a. And looking at what is left, it's a binomial. So we can only have two possibilities. It's either a difference of two squares or the difference or sum of two cubes. In this case, it's obvious that a squared and 4b squared are perfect squares. So this is the first case, a difference of two squares. Remember that when you have a difference of two squares, the first thing on your mind should be plus minus. And then, square root of a squared is a. Square root of 4b squared is 2b. Let's write them here. And then, copy both terms to the next binomial. Now, let's check some more if we can even factor this further. So looking at the first binomial, the terms are neither perfect squares nor perfect cubes. So, it's already a prime polynomial. Checking at the second binomial, the terms are also neither perfect squares nor perfect cubes. So, they're also prime na. Therefore, we have finally completely factored this binomial. We can check by multiplying all factors. Let's look at example number 2. What if we're asked to factor completely the trinomial x to the 5th minus 3x to the 4th minus 10x cubed? According to our visual guide, the first thing that we should do is look for the GCMF, kung meron. In this case, by observation, there is no common numerical coefficient among all terms. But looking at our literal coefficients, x cubed is common among them. So, yun na yung GCF. You factor x cubed out. To get the other factor, divide each term by the GCF x cubed. Let's try. X to the 5th divided by x cubed is x squared. Use the rows of exponents. Negative 3x to the 4th divided by x cubed is negative 3x. And negative 10x cubed divided by x cubed by rows of exponents is negative 10. So, this results to a factored form of x cubed times the quantity x squared minus 3x minus 10. You can check, of course, by distributing x cubed. But let's see if we can factor this further. Let's copy x cubed here. Looking at what is left, it's a trinomial. So, we have three possible cases. Every quadratic trinomial can be factored naman by organized listing. However, there are cases where we can use a faster and more systematic method. So let's check the trinomial if it's the first, second, or the third case. Let's check if it's the first case where the leading coefficient is equal to 1. By checking, the numerical coefficient of the first term is indeed 1. So, it's the easiest case. It's the first case. We set up the binomial factors here. And surely, x are the first terms and we need only to find the constants. Remember that we can only use this technique if the leading coefficient is 1. Now we need to ask, what are the factors of c with sum equal to b? Since c, the constant, is negative 10, we try to find a factor pair of negative 10 that adds up to b, which is negative 3. So, what are the factors of negative 10 with sum negative 3? Let's list these factor pairs. We start from 1 times negative 10, and of course, we consider their opposites. But none of these two factor pairs add up to negative 3. Let's try 2 times negative 5, and their opposites, negative 2 times 5. We observe that 2 and negative 5 have a sum equal to negative 3. So we use these and place them here. Now, let's check some more if we can even factor these binomials further. Looking at the first binomial, the terms are neither perfect squares nor perfect cubes. So it's already prime. And checking the second binomial, the terms are also neither perfect squares nor perfect cubes, so it's already prime din. Finally, we have a completely factored binomial. The factors are x³ times the quantity x plus 2 times the quantity x minus 5. We can check by multiplying all the factors. Now let's look at the third example. What if we're asked to factor completely 32x³ minus 16x² plus 2x? According to our visual guide, the first thing we should do is look for the GCMF, the greatest common monomial factor, kung meron. In this case, by observation, 2 is the GCF of the numbers 32, negative 16, and 2. Let's factor 2 out. Looking at our literal coefficients, x is common among them. So, yun na yung GCF. Our GCF is 2x. To get the other factor, divide each term by the GCF 2x. 32x³ divided by 2x is 16x². Negative 16x² divided by 2x is negative 8x. And finally, 2x divided by 2x is 1. This results to a factored form of 2x times the quantity 16x² minus 18x plus 1. You can check, of course, by distribution. Now, let's see if we can factor this further. Looking at what is left, it's a trinomial. So, we have three possible cases. Let's check the trinomial if it's the first case where the leading coefficient is equal to 1. By checking, unfortunately, the numerical coefficient of the first term is not 1. It's 16. Sayang, it would have been the easiest case sana if it were the first case. Now, don't worry, we have other cases. But don't get too excited and immediately use organized listing or AC method. Let's check if it's the second case first, if it's a perfect square trinomial. Now, remember the patterns? Question 1. Is the first term, 16x² a perfect square? Yes, it is. Its square root is 4x. Question 2. Is the last term, 1, a perfect square? Yes, it is. Its square root is 1. But another possibility is negative 1. Consider also negative 1. But we're not yet done. Let's check the middle term. Next step, get double the product of the two square roots. So, we multiply 2, double, times 4x. And let's consider negative 1. Question 3. Is this equal to the middle term? Yes, it is. 2 times 4x and negative 1 is negative 8x, our middle term. So, it's a perfect square trinomial and it's very easy to factor. Now, don't forget to copy 2x first. Lagay natin dito. And then we simply set up the factors of this PST. It will be a binomial squared. And then put the square roots of the first and the last terms here. PST factored. But let's check some more. Baka we can factor these binomials even further. For the binomial, the terms are neither both perfect squares nor both perfect cubes. So, they're already prime. Finally, we have a completely factored polynomial. The factors are 2x times the quantity 4x minus 1 squared. We can of course check by multiplying all the factors. Let's look at the fourth example. Now, we're going to factor this trinomial completely. Remember that factor completely means we must continue until no more expressions can be factored. Step 1. a should be, is to factor any greatest common monomial factor. So, let's find the GCMF here. We look at 18, 15, and 12. The greatest common factor for these numbers is 3. Next are the variables. We look at the x and y variables. For the x literal coefficients, x to the fourth, x cubed, and x squared, the common factor is the lowest exponent, which is x squared. For the y literal coefficients, y, and y, the common factor is simply y. So, our GCMF is 3x squared y. Now, we divide each term by 3x squared y. 18x to the fourth y divided by 3x squared y is 6x squared. Divide 15x cubed y by 3x squared y, it's equal to 5x. Lastly, negative 12x squared y divided by 3x squared y is negative 4. The factored form is now 3x squared y times the quantity 6x squared plus 5x minus 4. Now, we need to focus on the remaining quadratic trinomial, 6x squared plus 5x minus 4. This is not the first case since the leading coefficient is not 1. This is also not a perfect square trinomial since the leading coefficient 6 is not a perfect square. This is then the last case. We can use either organized listing or AC method, but we use the more systematic one, the AC method. Step 1. Identify A, B, and C. So A is 6, B is 5, and C is negative 4. Next, calculate the product AC. So AC is 6 times negative 4 or equal to negative 24. Now, we need two numbers that multiply negative 24, the AC product, and add up to positive 5, the B term. If we try 1 and negative 24, they add up to negative 23, not equal to 5. Their opposites also don't add up to 5. If we try 2 and negative 12, they add up to negative 10, not equal to 5. Their opposites also don't add up to 5. If we try 3 and negative 8, they add up to negative 5, still not equal to 5. However, their opposites, negative 3 and 8, multiply to negative 24 and they add up to 5. So, these are our numbers, negative 3 and 8. We can then split the middle term here, itong 5x, with our two new terms, negative 3x and 8x. So, we copy 3x squared y here, and then we write 6x squared minus 3x plus 8x minus 4 using negative 3 and 8. Split up 5x done. Now, we use factoring by grouping on the 4-term polynomial. Group the first two terms and the last two terms. So we copy 3x squared y, and then we write the group 6x squared minus 3x, that's one group, and 8x minus 4 as the other group. Now we copy again 3x squared y. But this time, let's factor the first group 6x squared minus 3x. We see that the GCMF is 3x. So, we write 3x times the quantity 2x minus 1. Next, we factor the second group 8x minus 4. We factor out a GCF. Subukan natin to factor out negative 4. If we do that, we now have negative 4 times the quantity negative 2x plus 1. However, remember that our aim is to factor out a common binomial factor. Problema, 2x minus 1 here is different from negative 2x plus 1. So, hindi sila common, we cannot factor them out. So, factoring out positive 4 brings us to a dead end, unfortunately. However, if we just copy the first part here, and instead factor out 4 here, we can achieve our aim, a common binomial 2x minus 1. So, we disregard our first try at factoring out a GCMF. Now, we copy 3x squared y again and do the final grouping step for the terms. Since we now have a common binomial factor 2x minus 1, we factor that out. Finally, we bring back the GCMF we found in step 1, 3x squared y, and the completely factored form of the original trinomial is 3x squared y times 2x minus 1 times the quantity 3x plus 4. Whew! So yun na yun. Always remember to check for a GCMF first kung meron, then you may use any method. In this case, we use AC method if we have a quadratic trinomial remaining. Example number 5. Factor 3x to the 9th minus 48x completely. Okay, the very first rule of factoring is always to look for the GCMF. Let's find the greatest common monomial factor for this binomial. Numerical coefficients first. We look at 3 and 48. Since both 48 and 3 is divisible by 3, the greatest common factor is 3. Literal coefficients next. We look at x to the 9th and x. X has an exponent 1, of course. The common factor is the term with the lowest exponent, which is x. So, our GCMF is 3x. Let's factor that out. Now, we divide each term in the binomial by 3x. 3x to the 9th divided by 3x is x to the 8th. Negative 48x divided by 3x is equal to negative 16. The factored form is now 3x times the quantity x to the 8 minus 16. What we have now is a binomial here. Remember that there are only two possibilities. It's either a difference of two squares or a sum or difference of two cubes. So let's copy 3x first, and then, looking closely at x to the 8 minus 16, is this a difference of two squares? Let's check. Let's ask, is x to the 8 a perfect square? It's a variable with even exponents. So, square root of x to the 8, copy the variable x, and simply divide the exponent 8 by 2. It's x to the 4th. It's a perfect square. Question number 2. Is 16 a perfect square? Yes, it is, because square root of 16 is 4. We see that it's a difference of two squares. Therefore, we can factor it. Looking at the formula, we set up the binomial factors, and the first thing on our mind should be plus and minus. Write the first square root here, and then copy here. Then write the second square root here, and then copy here. Currently, we have these factors. However, we should still check if we can factor any of these two binomials pa rin. Checking the first binomial, x to the 4th plus 4, the terms are not perfect cubes. Let's check if it is a difference of two squares. Looking at the first term, x to the 4th, is it a perfect square? It's a variable with even exponents, so square root of x to the 4th, copy the variable x, and simply divide the exponent 4 by 2. It's x squared. It's a perfect square. And then obviously 4 is a perfect square with square root equal to 2. However, the first binomial is not factorable because it's a sum of two squares. And it's definitely prime. Wala pong sum of two squares na factorable polynomial. But looking at the second binomial, it's a difference of two squares uli. So, let's put all the factors together. We keep the GCMF, 3x. We keep the prime factor, x to the fourth plus 4. And we replace x to the fourth minus 4, a difference of two squares, with, let's set it up, two binomial factors. And looking at the formula again, let's put plus and then minus. Then copy the square roots of the two terms here. The terms of these binomial factors are now neither perfect squares nor perfect cubes, so they are already prime. So, the completely factored form of 3x to the 9th minus 48x is 3x times the quantity x to the 4th plus 4 times the quantity x squared minus 2 and the quantity x squared plus 2. And that's how you factor this completely. Now let's factor this 4-term polynomial completely. The first step is to look for a GCMF, a common factor. In this case though, there's none. So may mga cases talaga na walang GCF. Since this is a polynomial with 4 or more terms, we now use factoring by grouping. What we need to do is arrange and group the terms. Remember that factoring by grouping may involve several trial groups before we can successfully factor them. We try first grouping these terms into 2. We'll group the first 2 terms together and the last 2 terms together. We need to rewrite the expression slightly to make the grouping clear, especially when dealing with negative signs. We can rewrite the expression and convert negative 2x to plus quantity negative 2x. Remember that doing this still makes it equal to the original polynomial. So we now have xy minus 5y plus negative 2x plus 10. Now, we create our two groups. Quantity xy minus 5y is the first group, plus the quantity negative 2x plus 10 is the second group. And yes, converting negative 2x to plus negative 2x ensures that we can put the grouping symbol just before it and makes it equal to the polynomial on top. Next, we find the greatest common monomial factor for each group. Group 1, xy minus 5y. The common factor is y. We can factor y out. We get y times the quantity x minus 5. Plus, we look at group 2. The common factor for the numbers negative 2 and 10 can be 2. Let's try factoring out a positive 2 first, just to see what happens. So we have 2 times the quantity negative x plus 5. But if we look at our binomials, we have x minus 5 here and negative x plus 5. They are close but not exactly the same. They are actually opposites. Remember that our aim in factoring by grouping is to get a common binomial factor which we can later factor out. Sorry, with 2 factored out, we reach a dead end. So, we can adjust the GCMF to match the binomial. Let's go back, copy the first part, and adjust our factoring for the second group, negative 2x plus 10. But instead of factoring out positive 2, let's factor out negative 2 this time. When we divide negative 2x by negative 2, we get x. When we divide plus 10 by negative 2, we get negative 5. So, the second group factors to negative 2 times the quantity x minus 5. And we now have a matching, a common binomial factor, x minus 5. But our full expression is not yet completely in factored form since we still have a plus sign here. But since we have successfully created a common binomial factor x minus 5, this is the final step in grouping. We factor out this common binomial x minus 5, and what is left over forms our second factor y plus negative 2. Finally, we simplify the second factor by removing the brackets and the plus negative sign. Thus, the completely factored form is the quantity x minus 5 times the quantity y minus 2. And that's how we factor a 4-term polynomial completely using the factoring by grouping method. But before we fully leave this polynomial, as we know, we can group other terms as well to try and factor by grouping. So, let's take a second look at this. Let us find another way of factoring by grouping xy and negative 2x instead. Pause this video now to analyze a second way to factor this and get the same factors as the previous grouping. Nakita ba? Okay. Another way, the last way to group the terms is by grouping xy with 10 instead. Pause this video now and analyze. Notice that we see that grouping the terms like so won't yield any GCMF since the group terms will have nothing in common. There's no GCF and an unsuccessful attempt at factoring. No worries though, as we have successfully factored the polynomial using the first 2 tries. With these 6 worked examples, I hope you got to have a feel on how to do factoring polynomials completely. Now it's time to try this on your own. Here are several exercises and subukan nyo nga. Try to pause this video now and solve them. Kaya nyo yan! Go! Here are the factors. I hope nakuha nyo lahat. Now, this concludes our tutorial series in factoring polynomials. Remember to come back and look at our timestamps in the description below whenever you need to practice specific techniques. Don't forget to like and subscribe. Happy solving!